Thank you for joining us in our fifth installment in our series on cement soil stabilization. The series is based on the Portland Cement Association's Guide to Cement Stabilized Subgrade Soils. The primary purpose of the guide is to describe the characteristics, uses, and benefits of cement stabilized subgrade and present methods for geotechnical evaluation, mix design, construction, and field testing that will produce a satisfactory project. This presentation will provide you information regarding the process for constructing and field testing of cement soil stabilized projects. We will discuss the required equipment needed for construction, different construction methods, environmental and safety considerations, and field inspection and testing methods. Let's get started. We will begin today's presentation reviewing the objectives. Today's objectives are to understand the equipment requirements for the cement soil stabilization process, understand the steps in the construction process itself, awareness of environmental and safety considerations with the cement soil stabilized project, and understand the process of field inspection and quality control on a cement soil stabilization project. Cement soil stabilization is used to improve the soil's strength and stability. It's a common choice for construction projects because it's cost-effective, durable, and can be completed quickly. The inclusion of the geotechnical engineer in the pre-construction phase and throughout the construction process is critical to ensure that the recommendations in the geotechnical report are being met. Now, keep in mind that there are always two paths which can be taken to use cement to improve the subgrade soil. When marginal conditions are foreseen before the construction begins and sufficient time is available for adequate field testing and laboratory testing, the cement soil stabilization application is considered to be on the design path. Although, when unforeseen marginal conditions are encountered during the construction process and an immediate solution is required, cement-based mitigation can be expedited with engineering judgment, previous experience, or an abbreviated laboratory and testing program. There is no doubt that various pieces of equipment are required for the placement of cement soil stabilization. They consist largely of common roadway construction machinery, though the reclaimer or mixer is needed to uniformly mix the cement into the native soil. The following equipment is recommended: reclaimer or mixer, grader, cement or slurry spreader, sheep's foot roller, water tank for dust control, smooth drum roller, and a pneumatic tire roller is optional. The construction techniques for cement soil stabilization are very similar to those of a mixed in place cement treated base or full depth reclamation. The timing of the operation is less stringent when dealing with cement soil stabilization. Consideration must be given to preparation before the mixing operation. Guide stakes should be set to control the area that is to be stabilized with the cement, and it also is important to ensure that each truck places the required amount of cement in the appropriate area. The first step in this construction process begins with removal of the existing surface material. This includes vegetation, existing pavement, any granular base material, or any other undesirable material that has been identified in the geotechnical report. Based on the soil conditions at the time of construction, the percentage of cement to be added may also be adjusted if necessary. The steps included in the construction process are moisture conditioning if necessary, initial pulverization of the subgrade if necessary, preliminary grading, the cement application, mixing in the cement, achievement of optimum moisture content of the subgrade, compaction, final grading, and curing. Let's look a little deeper at each of these steps of the cement soil stabilization process. The subgrade should be tested to determine the moisture content at the beginning of the construction operation. For highly plastic soils, mix the cement in dry or in slurry form prior to adjusting the water content to bring the soil to optimum moisture content. This may prevent the clay from balling and failing to provide the desired results. For overly wet soils, aeration of the soil may be necessary prior to the stabilization process. That way, the soil can be pre-treated with a moisture absorbent additive. For soils that are dry or too dry, water can be added immediately before or during the initial pulverization process. A moisture content near the optimum mixture content can facilitate the pulverization process, especially for highly plastic soils or expansive clays. Initial pulverization is not always necessary, but in cases where it is necessary, this process refers to the step where existing soil is thoroughly broken down into smaller particles using specialized machinery, essentially creating a fine, uniform mixture before adding cement and water to achieve stabilization. It's a crucial step to ensure even distribution of the cement binder throughout the soil mass. As stated, the purpose is to break up those large soil clumps and create a consistent texture for optimal mixing with cement. Now, typically this is done using a specialized machine like a road reclaimer or a scarifier that grinds and tears up the soil. This step is important as proper pulverization is essential for achieving a strong and uniform soil cement mixture. It's important to sufficiently pulverize the material to the full depth and width of mixing, especially for cohesive soils such as silty clays and clays. In the final mixture, 100% of the material should pass the 1.5" sieve, and at least 60% should pass the number 4 sieve. Now, this does not include any gravel or stone retained on the number 4 sieve. And finally, the soils that were pulverized, the more effective cement stabilization treatment will be. The crown and grade of the planned roadway or pavement should be noted, and grading should be completed as necessary to match the construction drawings. Now, take care not to remove too much material at this stage because it's easier to remove material than add after the cement is applied. The grade at the start of the mixing should be similar to the final grade after mixing. However, it should be taken into consideration that the volume of the subgrade and therefore the grade elevation may increase slightly with the addition of the cement. A dry condition is typically the condition that most cement is applied. The cement should be uniformly spread in a controlled manner by the spreader truck equipped with a mechanical spreader. Cement can also be applied in slurry form from a distributor truck equipped with an agitation system or additives designed to help the solids in suspension. The slurry form may also be applied from a concrete mixer truck. Most specifications call for the application of cement in terms of weight per area, such as pounds per square yard. The percentage of cement needed is based on 3 factors: the in-place dry unit weight of the native soil, the application rate specified, and the depth of the soil treatment. This equation calculates the spread rate based on the in-place dry unit weight of the native soil, the application rate specified, and the depth of the soil treatment. Remember that the percentage of cement to add was calculated and confirmed in our mix design phase of the process. The dry unit weight and the depth of remediation was also determined during the geotechnical evaluation phase of the process. This chart, adapted from Halstead and Hall from 2008, shows the typical spread rates in the United States. It is based on a percentage, and as you can see, the dry unit weight of the soil is in the left-hand column, while going across the top, we see the spread rates based on the depth and pounds per square yard. As an example, if we have a dry unit weight of 100 pounds per cubic foot and are looking for a spread rate of 30 pounds per square yard at 10-inch depth, the spread rate would be approximately 4%. Depending on the weather and/or location, dust control may be an issue if the cement is applied in a dry condition. The most important time for dust control is immediately before the applied cement impacts the ground. Dust is typically not a problem once the cement is on the ground, except on a very windy day. Cement spreading equipment typically has adequate controls to minimize fugitive dust during the spreading operation. If utilizing the cement slurry application, it's important that the slurry be dispersed uniformly over the subgrade area so that it does not run off or pool. Sometimes it's necessary to construct berms along the edge of the treated area to confine the slurry. After the cement is spread over the surface of the subgrade, the next step is to mix the cement into the subgrade material using equipment such as a reclaimer. This mixing should begin within 30 minutes of the placement of the cement. Remember, it's important to sufficiently pulverize the soil to the full depth and width of the mixing area, especially for those cohesive soils such as silty clays and clays. The finer the soils are pulverized, the more effective the cement stabilization treatment will be. Here is a chart that compares the typical gradation requirements for cement stabilized subgrade, cement treated base, and full depth reclamation. If the natural soil does not meet the gradation requirements, it may be blended with coarser or finer materials to achieve the desired gradation. For your information, the following equipment is not recommended for pulverization of the subgrade: agricultural discs, graders, rippers, and other scarifying equipment. The reason being is they cannot achieve the proper degree of pulverization needed. A reclaimer is the correct equipment for the job. It uses a mixing drum operating in an upward cutting direction to finely mix the cement, existing subgrade soil, and additional water if required. You want to continue mixing until the soil is uniform in color, meets the material sizing requirements, and is at a moisture content that allows compaction to the required density. This process of spreading the cement, applying water if needed, and mixing should result in a uniform mixture of cement, soil, and water for full design depth and width. So, how do we know the proper depth of mixing? Well, this is a function of design, site conditions, and available equipment. Reclaimers now have the capability of uniformly mixing up to a depth of 2 feet. However, if greater depths are required, the subgrade can be treated in multiple layers. If this is the case, we remove the upper layer, and treatment of the bottom layer can be completed. Then the upper layer is replaced and also treated. This obviously is a more costly process than single layer treatment, but may be necessary depending on the depth. An option to be considered when deep treatment is necessary would be to add a cement treated base on top of a single layer of cement soil stabilization. As stated earlier, it's very important that the moisture content of the subgrade be maintained in accordance with the recommendations in the geotechnical report until the material has been covered with base material or pavement. As seen in this diagram, water is added by injecting the proper amount of moisture into the mixing chamber of the reclaimer or by placing the water on the ground with a water truck in a separate operation. In either case, obtaining the correct amount of moisture is very important for achieving the target compaction, particularly in expansive clay soils. The process continues. The next step in the cement soil stabilization process is compaction. The time limit between mixing and compacting is not as stringent for the soil cement stabilization process as it is for the cement treated base. Although, if possible, compaction should occur immediately after mixing, and all cement soil stabilization construction operations should be completed on the same day. Each compacted lift should meet the density requirements and the optimum moisture content requirements stated in the geotechnical report or any applicable specifications. Meeting the density requirements is very important because the primary purpose of cement soil stabilization is to provide stability and satisfy compressive strength requirements. If unable to achieve compaction in a single lift of cement soil stabilization due to the unstable conditions, Multi-lift construction may be necessary. If you have a severely unstable area, a test strip should be constructed to determine the number of lifts required. If achieving a specified density is prohibitively difficult, a stable, firm, and unyielding subgrade condition may also be accepted by the project engineer. If the soil consists of silty or clay materials, initial compaction should be done with a vibratory tamping roller or a pad fit roller that compacts from the bottom to the top of the subgrade. This type of roller should continue until the required minimum density of compaction is achieved, which is usually indicated by the pad foot roller walking out of the impressions it leaves in the soil. If the material being stabilized consists of sand or graveling materials, a vibratory smooth drum roller or a pneumatic tire roller should be used. For both types of material, the cement soil stabilization material should be uniformly compacted to a minimum of 95% of maximum dry density. As a final check, a proof roll by a tandem axle truck loaded to the legal maximum limit may be performed to ensure an adequate and uniform cement soil stabilization treatment. As compaction nears completion, the surface of the cement soil stabilized material should be shaped to the specific lines, grades, and cross sections. Remember, it's typical to slightly overbuild the surface so there's no need for thin fills and makes it easier to achieve that final crown and grade. Compaction shall then continue until uniform and adequate density is achieved. The compaction and finishing process shall be performed in such a manner as to produce the dense surface free of compaction planes, cracks, ridges, or loose material. All of these finishing operations should be completed within 4 hours from the start of mixing. Unfortunately, although not always done in practice, curing is suggested to obtain the maximum benefit from the cement treatment. If required by the engineer or design professional, the surface should be moistened with fog-type water spray or a bituminous emulsion after the final finishing is completed. As always, safety and environmental considerations must be examined. The cement soil stabilized material should never be mixed with standing water or when the soil or aggregate is frozen. Cement soil stabilized material should never be mixed when the air temperature is below 40 degrees Fahrenheit. It's further recommended that the dry cement should not be placed on windy days. The cement could be lost and the blowing cement may cause a dust nuisance to the general public. When handling cement, always wear proper protective gear, including eye protection and protective clothing, which would include gloves, long sleeve shirts, and long pants. Cement is a caustic material and protection is necessary. The inspector assigned to the cement soil stabilization project should monitor and/or verify the following items: cement content, application rate, moisture content, mixing depth, compaction, and curing. More information on inspection requirements may be found in further detail in the Soil Cement Inspector's Manual, published by the Portland Cement Association in 2001. The owner's representative should conduct quality control on site with the assistance of the geotechnical consultant. At a minimum, a quality control program should include the identification of unstable areas. These areas can be identified during the proof rolling and should be evaluated by the contractor and geotechnical consultant to determine the depth of the treatment required. Samples of the unstable material should be obtained for laboratory testing at this time to determine the percentage of cement required for the stabilization. Before any cement is applied to the subgrade, all of the equipment should be inspected to make sure it is in good working order. The inspector should verify that all cutting teeth of the reclaimer are in place and in good condition. The spray bar nozzles are working properly and not clogged, and the onboard stabilizing agent system is functioning and accurate. ensure that the water application rate is correct. If a bulk spreader is used, it should be properly calibrated. A test strip may be constructed to monitor the cement application rates and depths of treatment. This should be done after the contractor's methods have been established and the field observations performed. The application rate should be monitored to ensure accuracy. The mixing should begin within 30 minutes of the cement placement. The effective index of mixing should be verified during this operation to ensure that the proper gradation and pulverization depth is achieved. Compaction rollers should be inspected to ensure that they have the proper operating weight and working water systems. The scrapers should be inspected to ensure that they meet specifications. Compaction should occur immediately after the reclaimer mixes the cement and the subgrade. The field density testing should be performed during the construction in accordance with approved AASHTO or ASTM methods. This will confirm that the project specifications are being met. Consideration should be given to testing for density and moisture on a regular basis. For example, maybe every 5,000 square feet for each compacted lift of material. And lastly, curing should be performed according to the project specifications. I would like to thank E.J. Brenneman, LLC from Berks County, Pennsylvania, for providing drone footage of a lime soil stabilization project they completed in Mansfield, PA. A reclaimer is blending the lime with the soil. The footage captures the machine in motion, turning over the soil and lime mixture to achieve a consistent blend. If necessary, water may be added during the mixing process to activate the lime. As you can see the importance of achieving the correct moisture content for optimal stabilization. Please note, there is very little dust. We also see a pad foot roller being used to compress and compact the stabilized soil, and a smooth drum roller creating a smooth compacted grade surface. While this series has been focused on cement soil stabilization, we would be remiss if we didn't mention another product that could be used in soil stabilization: lime. The choice between cement and lime to stabilize soil depends on several factors related to soil type, project requirements, environmental conditions, and performance goals. Cement is best for granular soils with low plasticity, such as sand, silt, or silty clay. It binds particles together by forming that hard cementitious matrix, while lime is best for high plasticity clays and soils with a significant amount of fines. Lime reduces the plasticity, shrinks swelling potential, and improves workability by altering the soil structure. Lime requires a sufficiently high pH to facilitate the chemical reaction between calcium hydroxide and the silica alumina in the soil. If the soil has a low pH or a high organic content, lime may not be effective. While cement is less sensitive to the soil chemistry, making it more versatile for stabilizing a wider range of soils. Cement provides a higher strength and is ideal for applications needing a strong, rigid base, while lime enhances soil workability and provides moderate strength improvements. It's often used in cases where long-term durability or swelling control is the focus. Lime is better at improving the workability of wet, sticky clays, while cement may make soils brittle if over-applied. Cement stabilizes soil faster, with noticeable improvements in hours to a few days, while lime stabilization often requires longer curing times, days to even weeks, to achieve that full strength and plasticity reduction. Lime performs well in wet conditions as it reacts with water and can help dry out excessively moist soils, while cement works better in moderately moist or dry conditions, since excessive moisture can hinder its ability to cure properly. Cement-treated soil is more durable in high traffic or erosion-prone applications due to its rigidity, while the lime is better suited for areas with expansive clays and cyclic wet-dry conditions, as it reduces the swelling potential. If sustainability is a major focus on your project, lime has a lower carbon footprint compared to cement, making it a preferred option for the project's focus on sustainability. Cement is more energy intensive to produce and therefore contributes more to greenhouse gas emissions. Lime may be more cost effective for projects where soil plasticity reduction or moisture control is the main goal. Although cement can be more expensive, but it may be justified for projects requiring higher strength and quicker stabilization. Laboratory testing, such as the Atterberg limits, Proctor testing, and unconfined compressive strength tests in conjunction with small-scale field trials are often necessary to determine the most effective stabilizer for a specific soil and product. If you would like more information on cement soil stabilization, please refer to the following: Guide to Cement Stabilized Subgrade Soils, published by the Portland Cement Association, May 2020. PCA Soil Primer, published by the Portland Cement Association in 1992. PennDOT Publication 408 Specifications, published October 11, 2024. Soil Cement Laboratory Handbook, published by the Portland Cement Association in 1992. Guide to Cement-Based Integrated Pavement Solutions, published by the Portland Cement Association in 2014, and the Soil Cement Inspector's Handbook, published by the Portland Cement Association in 2001. Thank you for joining me today to learn more about the importance of construction, field inspection, and testing for cement soil stabilization, and how they ensure that the soil is stabilized correctly and the structure is safe. For more information, please contact me at the Pennsylvania Aggregates and Concrete Association. Thank you and have a great day.